Welcome to the webinar. You have as an attendee in listen-only mode.
Slab of 2 meter 6. Here in show calculation results, we also can see the center of the section. This is useful when we have to choose the offset of the for the correct application of the slab element. The beams have been divided, as we can see here, in elements of 1 meter's length to easily keep the control of distances along it. Now we go in top view, and so I can show the boundaries. Okay, the scheme has been chosen for allow the thermal expansions in both x and y direction, releasing the degrees of freedom for this support in x direction, for the y direction in this support, and both direction for the third one. The first is fixed. In this way, we prevent stresses due to uniform temperature load. We can see that in this model we didn't create the substructure. Now we can see the load applied. Okay, we have the permanent loads like self-weight. We have the parapet load, that is element load applied with an eccentricity. The pavement load that is applied directly on beams. Then we have wind load. We saw in the slides how to calculate it. This is applied on both horizontal direction, and it is applied with an eccentricity, as we can see here, considering the presence of vehicles on the carriageway. The uniform temperature load, now I can show you. Okay. That is calculated with the uniform temperature is applied on every element present in the model, and is calculated with maps that we can find in the Romanian code. The gradient temperature is applied directly on beams. We have a positive one and a negative one, depending on which one is the warmer side of the beam. The traffic effect has been modeled with the moving load optimization function. It's a traffic lane for this model. The moving load optimization function automatically finds the most onerous disposition of the lanes in the transversal direction. In this project, we have a 4 meter and 0.5 carriageway. And in this model, we use the cross-beam distribution of vehicles, since we create a group of a structural group that is made of beams, of these transversal elements. Then the vehicles considered are those defined by the aero codes, and here we can see also the C factors. That they are useful for apply frequent values for frequent combination of load model 1, and we define the moving load cases. We define the characteristic load model 1 case. This is for to create the group 1A of the table that we have seen in the slides. Then a frequent one to combine with the horizontal traffic loads. In this case, we ignore C factors, we consider it. And finally, LM2 useful for the group 1B. Let's see how now this horizontal traffic force. We have here braking loads. That is and the acceleration that is in the opposite direction. They are distributed in the longitudinal direction where the first lane is supposed to be. And centrifugal force, we also apply the centrifugal force to both beams. And this is applied because the bridge has a radius of curvature of 170 meters. All these horizontal forces are applied at the level of the carriageway as required by the code. Now we can check the results. The analysis has been already run. We can see, for example, moving tracer. This is interesting. Moving tracer shows the most onerous disposition of traffic load for each element. This is also a sort of test for the accuracy of the model. For example, we want to see the configuration of frequent load for maximum moment of the element 80. The element 80 is placed at the center of the span. We include C factors, and this is the configuration of a load model 1 frequent. We can see the reduced value of the axis, and that the most loaded part is in the center as expected. Also, we can see, for example, the maximum effect in moment for LM2. It seems correct, and one characteristic. Also, we can see the resultant moment in beam forces moment. For example, we can see the effect of set weight on the structure. We see that the deformed shape is coherent. We have, for example, the effect of wind load on one side. Okay. And for example, we can test the temperature, uniform temperature. You can see if the disposition of supports as it worked. And as we can see, we don't have bending moments due to the freedom of the bridge to expand. Okay, so on we can, for example, see the effect of the LM1 characteristic. And so on. And so we have seen the first model build. This is the simplest one. Now we come back to our PowerPoint. With the first model, considering the wall deck package, we reach a section of about 1.6 meters. Due to the presence of an underpassing intersection, we had limited space. In addition, the ramp needed to be shortened since in the first version of the project, it got too close to some buildings near the road. This further reduced the available clearance, making the first section no more suitable. The proposed solution was a continuity with a single tab section as main beam, still keeping a central span of 55 meters. Tab and box girders are more expensive and complex to realize. The difference between a box and a tab section is that the second one is opened in the upper part. These kind of sections have the advantage of a reduced height compared to the resistance, as well as a great resistance to torsion. Closed sections are economically viable only for reduced deck weights. And for our project, seemed the perfect solution due to the limited space and the reduced dimensions of the bridge deck. In this phase, substructure has been modeled in MIDAS, and the effect of the seism has been analyzed. The Romanian code P100 that is included in the program provides some maps to identify the location where the structure is and to obtain the values of the corner period TC and the acceleration of ground level AG. Knowing these two parameters, we have almost all ingredients to execute a response spectrum analysis. Aerocode 8 part 2 requires a behavior factor for limited ductile piers equal to 1.5. Modal shapes have been combined in model through a complete quadratic combination, CQC, that is more suitable for multi-span bridges respect to SRSS, that is more commonly used, but tend to overestimate or underestimate the results in a system with close natural frequencies. As we said, the model is realized with a single composite section. We have three spans of 20, 55, and 20 meters. Since we will analyze the seismic behavior of the structure, it's important to check in the structure tab the convert self-weight into massive option. Here we can choose also to consider the masses as concentrated or distributed. We choose the distributed one, the consistent masses option, that is for a more accurate model. The main girder is a composite steel pipe section. You can see here the properties. The total weight of the steel part is 1.2 meters, while the wall slab is included directly in the section. Due to its width of nearly 3 meters, we had some stiffness. You can see it here in the bottom plate to prevent local buckling phenomenon. The piers are modeled as a plate element here with a thickness of 2 meters and fixed to the base, as you can see. The connection between the beam and substructure is realized with elastic links, freeing the longitudinal direction to allow the thermal expansion of the deck. In this model, we can see that we have applied permanent loads. Here we can see self-weight, sidewalk, that is the weight of the lateral part of the deck, and weighing surface. These loads have been converted in masses through the function load to masses. Here we can see. Okay, they are being added here. In this way, we can take into account these forces in the response spectrum analysis. As for the previous one, in this model we use the moving load optimization to simulate the traffic loads. Moving load optimization. We create a carriageway. In this case, since the model has any transversal element and just a single girder, we choose the vehicular load distribution as a lane element. Now, it's time to define the dynamic loads. We go in RS function. We define two the response spectrum, one for horizontal direction, one for the vertical one. Here we choose the design spectrum. We have P100 as an option here. Horizontal design spectrum. Here. And in the zone of Sinaia, we have TC equal to 0.7 and a ground acceleration of 0.3 g. This is the importance factor. For a strategic structure, we choose 1.4. And the bearer factor, as we see in the slides, is 1.5. Okay, this is how the response spectrum functions appears. We also define the vertical design spectrum. Okay, the option is the same. Here we have to choose vertical design spectrum and use the same factors. Here is how it appears. We undefined also response spectrum load cases for the three directions of the seismic. We have RSX with an XY direction here, and the horizontal spectrum associated. RSY, that is the same of the first one, but you have an excitation angle of 90 degrees because it's a perpendicular direction, and the vertical component RSZ that has Z direction. Here we can choose the way we want to combine the modes. Preliminary operation before to define the RS load cases is to define the number of modes that you want to be considered by the programming the eigenvalue analysis options. Otherwise, here we won't have any mode to combine. We chose the CQC combination since we expect close natural frequencies between modes. Note that in the operation of combining modes, we lose signs. MIDAS gives the possibility to choose a method to assign them. Along the major mode direction, uses the sign of the major mode in cases where the torsion is significant or the modes are closely spaced, it is more appropriate to use along the absolute maximum value option. In any case, in our project, we left this option unchecked, being more conservative and leaving resultant forces in absolute values. Now we can see some results since we have the model already run. Here we can check the model shape, here in vibration mode shapes. Activating the legend, we can see, for example, the frequency, the natural period, and the effective modal mass for each mode. Okay, let's give a look to, this is the first mode, the second, and so on. We can see that the frequencies, the periods are quite close in this model. Now we can give a look to the forces, the forces moment for the girder actions. We can see, for example, the effect of the vertical seism on the moment. And for example, we can see the effect on fires with plate forces moment between fires and plate element. For example, we can see the horizontal action on the m-axis direction. Here is the one we can see, for example, the shear force. Now we go back in the presentation because we are going to talk about buckling. Lateral torsional buckling is a serious topic for metallic structures, but in composite section, generally, the slab connected to the steel partially mitigate the problem, acting as a constraint for the section which is not free to deform laterally. However, there are two ways in this phenomenon can be dangerous for composite bridges. The first occurs in continuous bridges, where the negative moment can compress the lower flange that is not constrained by the slab. And the second one can occur during execution, when the C-section is alone and we are casting the concrete of the slab. The buckling resistance of the steel members depends on its slenderness. That is a function of the critical elastic moment. European codes provide some closed form solution for these. We can see them here. But they all refer to double symmetrical section and the monosymmetrical T-sections. For our tab girder, the only way to calculate the M-critic value is through a buckling analysis, and for this MIDAS can help. We prepared a model of the tab girder we talked about. We import the section, in this case, from AutoCAD as a line element, and then we extruded it to realize the girder as a plate element. It's important to create a plate element because with a line one, we cannot catch all the possible deformation on the beam. We applied the boundary, so you can see it here. Display. We apply in a way coherent with the original model. We assigned a steel S355 as material, and we defined the thickness of the flanges and of the webs. Then we applied on the top flanges a notional load that we call the buckling. We choose a 10 kilonewton per square meter load. And we extend the analysis to 10 modes here in analysis, buckling. We choose 10 modes, adding the buckling load to the list. We already can give a look to results. We first check the moment associated with the load we apply in results. forces, plates, forces, moment. Buckling is the load we need. And we choose the normal forces. Right. Now we're gonna choose, for example, a central section of the girder. We isolate it. In this way, we can calculate the resultant bending moment, multiplying the forces with the distance from the center of section. Having this moment, bending moment, we have to multiply it for the critical load factor that we can find in mode shapes, buckling mode shapes. Here we have each mode analyzed. We can see different one. Okay, this is the first one. On the right, we can see the critical load factor for this mode. And also we have the next modes. Okay, this the minimum critical load factor of all modes that usually is associated to the first vibration mode, first buckling mode, has to be multiplied by the reference moment that we calculated, gives and giving us the elastic critical moment we look for. Well, also the second model is gone. Now we're gonna introduce the last one. For making viable the single tap girder solution, we needed an excavation at the level of lower National road of 15 centimeters. This made the second proposed solution not applicable due to logistical problems and to the excessive costs required for the work. To rise above the situation, a double tap section has been proposed and accepted. This solution has an high cost and weight, but gives the possibility to reduce the height of the deck package. Furthermore, to respect the available clearance requirement, we need to slightly modify the configuration of the intersection, achieving a reduction of the central span to 40 meters length. In this third model, phases of execution will be analyzed. This kind of analysis is crucial for bridges, since the way you plan to build a bridge can change in a significant way the resultant stresses in the elements. A delicate stage for composite bridges is the casting of the slab. In this phase, the deck is only metallic, so we can have various issues that will be ignored without studying step by step the structure. For example, the buckling problem previously analyzed. The Aero Code 116 prescribes some loads to consider for the casting phase. Mainly, we have the weight of the fluid concrete, the presence of workers and facilities, and formworks. This can be theoretically considered as a moving load because we don't know the most onerous position for the working area. In MIDAS, we could do this, converting this moving load in a static load through a specific function. Finally, we give a look to load combination considered in the model. Here we will show the Aero Code 0 ultimate limit state fundamental combination and seismic combination. Here we have the combination coefficients for road bridges from the NXA1. Also thermal uniform actions and gradients need to be combined between them using the factor provided by Aero Code 1.5 and the Nasional annex. Furthermore, the main direction of seism, marked as A in the seismic combination, are applied at the same time according to Aero Code 8. Okay, now we go in the MIDAS model. Here is mode. Piers are realized with a line element, with a section variable in both directions. We need to create a table group here. 4 table group for each pier to make the shape in the right way, since we have many elements to manage together. In this model, we used a non-common composite section that has been created with a specific tool of MIDAS, that is the sectional property calculator, and then imported as a sec file. Here you can see, for example, here is the section import. Here now we can see how it appears. This is the main beam, one of the two main beams. The slab is modeled with a plate element. Bold, okay, so you can see the wall structure. Okay, this is the slab, is a plate element, and this is done for a more accurate distribution of applied loads on it. For this reason, in this case, the moving load optimization has been done with a traffic load lane, traffic surface lane. Okay, this is already done. We have always a carriageway of 4.5 meters. We still use the load model provided by Eurocodes, and we created all load cases that we needed. These are the vehicles, load model 1, load model 2, and the moving load cases are characteristic, frequent, and load model 2. In this model, some loads along with traffic 1 have been applied as a surface load. As you can see, for example, for sidewalks, that is an edge surface load, and the action of the wheeling surface. The loads in case of execution are instead the beam loads. We created the concrete, the fluid concrete that are applied directly on beams, and the shear construction, that is the weight of the workers in casting phase. We applied this load directly on beams because in the phase when they are activated, the slab is not active at all. The one relative to the workers in our case was very simple, because having the minimum value of the expression for calculate the load, we have a uniform distributed load of 0.75 kilonewton per square meter, distributed equally between the two beams. Since the structure is a part of a bigger viaduct, the half lateral spans that we don't analyze are simulated with a nodal force. Okay, we can see here the load called pier. We applied it on a node located where the support is supposed to be, and the node is connected to the pier with an elastic rigid link. That okay, now we analyze the construction stages. We have a first stage of the duration of 30 days. That is the time needed by the concrete to reach its resistance and became an effective element. In this phase, piers are built and the other spans of the viaduct are installed. We activated piers elements, fixes at the base as boundary, and the group of load 0, that is composed by self-weight and the weight of the lateral spans. In stage 0, in stage 0, we plan to cast the concrete of the slab. We have all metallic elements we activated, with activating also the links between the deck and the piers. The load activated our group of load 1, including fluid concrete weight and the load due to workers. In the stage 1, we can activate the slab as an element, and we can deactivate the loads of group 1, activating instead the loads relative to the sidewalk on the last day, in this case. Finally, in stage 2, we set a duration of 100 years to see the effect of long terms. And in addition, we apply the weight inserted load of the group 2. Well, time-dependent effects has to be taken into account, especially for sections with parts in class 3 or 4, and for SLS checks. Since in these cases elastic analysis is required, and so the history of construction stages has an effect on final stresses. The time-dependent effects for the concrete can affect the deformations like creep and shrinkage, and the resistance with the increasing of compression strength in the past days after casting. We can define the laws and define this phenomena in properties here. Going in pre-shrinkage menu, we have already defined one law for our concrete 37. And we choose the code we want to repair. In our case, we choose European, and entering the FCK of the material and the humidity, or other than the notional size of the member, we have defined the relation, except for the age of beginning of shrinkage. Here, according to Eurocode 4 part 2, this duration is, this age is 1 day. And now we can show results and check the function rule. We have defined also the increasing of compression strength here, choosing always Eurocode as European code and entering, in this case, the FCM value. Here is the graph already drawn. And we see that we reach the full resistance practically in 30 days. Finally, we assign the time-dependent functions to our material with material is already defined. Then we check the properties of the composite section during construction stages. Here we have the two beams, the two main beams. Here, practically, we choose to activate the concrete part of this section in stage 1, and to avoid that the simultaneous presence of this part and of the slab element brings us to a double stiffness. We eliminated here in scale factor the torsional inertia in transversal direction y-axis. Okay, so we go to apply the same for the left beam. Then the Eurocode 4 part 2 provides that for continuous bridges, due to the negative moment on supports that cracks the tensile concrete, we have to not consider the stiffness of the slab of the 15% of the span on each side of internal supports. Then we are going to assign a zero stiffness for these elements, like here. To the plate stiffness scale factor, we defined also a stiffness reduction plate boundary group, and we put 0 on all these factors. This boundary group is useful to define for which load cases here in analysis boundary change assignments we are going to apply these modifiers. In this case, for example, we exclude the response spectrum analysis since it will not properly work otherwise. But we activate it for static load cases and moving load cases. So now it's time to check some results. In first place, we can check the construction stages if they work properly. Okay. We control that for each stage there are activated appropriate loads. Here we can see the first stage with only piers activated. Here we have the metallic elements activated. In stage 1 we have also the slab here, and we can see all the loads applied. And in stage 2 we have, this is the final stage, we have everything we need activated. The other loads automatically apply in the post-construction stages construction stages phase. Now, a little trick to save time when we need to create the load combination. You can see here we have any combination. The way is to take them from an existing file at the condition of using the same load cases names. For example, we have this existing file. It's an old file of another bridge. And we can export it in MCP file. That is the text form of the MIDAS file. We save it, we go find the load combinations here. We simply copy, and going back to the other model, we paste in the MCP commercial window. We go run, okay, and now we have all load combination already defined. Here we can check that we have done all we said in the slides. For example, we have all traffic groups, group 1A, group 1B, group 2. We have the envelope of all traffic loads. Then we have the ultimate link state combination. We have, for example, the combination between the thermal loads here, combined with wind in both directions, and with the traffic and the summation of the stresses of the construction stages. Then we have the seismic combinations for the three main directions, and the envelope of all seismic loads, seismic combination. Well, now we can see the traffic load effect in the moving tracer. Reinforces moment. Okay, we choose an element for the central span, for example, the 121. And here we can see the load distribution for maximize the LN1 characteristic. We see that in this case we haven't line loads, but they are surface loads. We can, for example, see the minimum, okay, and we see that it's coherent. And also, for example, we can see the effect on a side span, for example, for the element 45. This is the minimum, and this is the maximum value for element 1. It seems coherent. Then we inactivate the group no stiffness, because this they don't allow us to see real deformations. And then we give a look to the summation load for each stage. For example, we're going beam positive now. Okay, we go in the first phase with piers. Here we have only normal forces acting. Okay, then we can see for the stage 0, that is the phase when we activate the beams and the cross beams. For example, we can see the moment. Then we have the stage 1 with the add of the flab. And finally, we have the stage 2 with that is final stage, with also the pavement added. So we can see in the post-construction stages the load combination we defined. For example, we can see the envelope of the ultimate limit state combination. Okay. And also the seismic envelope. So this was the last solution proposed and finally accepted by the client for the realization of the work passage. As we have seen, MIDAS gave us the possibility to have a complete overview of different solutions, giving many options to choose the level of accuracy that we want to reach with our models, and having the flexibility to explore many solutions to find the most efficient. So I thank you for the attention. If you have any questions, please contact midasbridge@midassit.com.
perlu di sini dia mau izin kan, bukannya aspalnya ditaruh biar lebih itu kan. Toh ini kan dipegang buat